Hello, and welcome back to the I Heart Pluto Science Speakers Series. My name is Amanda Bosch. I'm a planetary scientist at Lowell Observatory and also the Chief Operating Officer. This week, we're celebrating the 92nd anniversary of the discovery of Pluto at the I Heart Pluto Festival. You can find more information about this festival by visiting our website, iheartpluto.org. We have events going on every day and night through Monday, February 21st, so come back and join us again. Prior presentations are also available to view at the same website or on our YouTube channel. Tonight, I'd like to say a big thank you to Fratelli's Pizza for sponsoring this science talk. And now I'm going to hand off hosting duties to my colleague, Dr. Jennifer Hanley.
Thanks, Amanda. I'm Jennifer. I am a planetary scientist at Lowell Observatory, and I study surface processes and the stability of liquids across the solar system. That ranges from things like water on Mars to the lakes and seas of Titan and glaciers on Pluto. So tonight, we're going to hear from Dr. Kelsey Moore. She is a geobiologist and astrobiologist with a focus on microbial life on early Earth and potentially on Mars. Her research centers around the ways in which microbes, through their biochemical makeup and their metabolic activity, interact with the environment. She is interested in how ancient microbes shaped young planets, and in parallel, how ancient environments impacted microbes and their evolution. She addresses questions related to the evolution of the biosphere on Earth and the preservation of organic matter and fossils. This includes investigations of microfossils and organic matter that were preserved during the Proterozoic and Archean eons, and experiments that shed light on the microbe-mineral interactions that may have promoted fossilization in ancient environments. As a member of the Mars 2020 science team and the Pixel and Sherlock instrument teams, she extends her research to the search for biosignatures on Mars. So we will take questions throughout the talk. Please feel free to type your questions into the YouTube chat, and we can answer them as we get to them. So welcome, Kelsey. We're looking forward to hearing about your work on searching for signs of life on Mars.
Thank you so much. And I will start sharing my screen now. Okay, thank you so much for the introduction, Jennifer. So my name is Kelsey Moore. As Jennifer said, I'm a postdoc at Caltech, and I'm also a member of the Mars 2020 science team. So today I'm going to be talking to you about the strive to search for signs of past life on Mars. And I'm going to talk a little bit about the research that I do on Earth, a little bit about Jezero crater, and the Perseverance Rover and all the instruments that are on board the rover. And as Jennifer said, I'm happy to answer questions as we go through the talk. So the Mars 2020 mission, this is an exciting day, or tomorrow is, because we are almost exactly at 1 year since the Mars 2020 Perseverance rover landed on Mars in Jezero crater. That was on February 18th last year. So this is a picture of Jezero crater. And the rover landed right about in here and is currently making its traverse kind of through this crater. And some of the mission goals of the Mars 2020 mission are to determine whether life ever existed on Mars, to characterize the climate of Mars, to characterize the geology of Mars, and finally, to prepare for human exploration of Mars. So these are all really important mission goals, but the one that I'm the most excited about as a geobiologist and an astrobiologist is determining whether or not life ever existed on Mars. So that's where we'll start. So this question, was there ever life on Mars? Was Mars ever habitable? Could it have hosted life? So what I'm showing you here is an image of what Mars looks like today. It doesn't look like a very friendly to life kind of place. It's very dry and arid. There's not very much water on the surface of Mars or inside of Mars. It is a very thin atmosphere, so it's constantly being bombarded with UV radiation. So it's not necessarily a habitable place today, but maybe in the past, when it looked more similar to Earth, it could have been habitable and it could have hosted life early on in its history. So let's talk about that concept of habitability for a minute, because this is really important before we start to talk about life and its preservation. So some of you may have seen this type of schematic before, this idea of the habitable zone, this kind of Goldilocks zone near a sun or a star. And this is the zone that's kind of just right in how close it is to a star. And we define a planet as being habitable if it has liquid water, shielding from UV radiation. So our Earth is shielded by our magnetic field and our atmosphere. And a planet also has to have nutrients and nutrient cycles. In addition to water that we need to live, we need nutrients. And the planet needs to have temperatures that are conducive to life. So it can't be so close to the star that it is too hot and burns up, or too far away so that it's too cold and the water is frozen and life can't exist at those temperatures. So in Mars's past, Mars does reside in that habitable zone around our own sun. And this image that I'm showing you here is an artist's rendition of what Mars might have looked like billions of years ago. And it might have looked more similar to the Earth. It might have had standing bodies of large water, oceans and lakes, and a thicker atmosphere than it has today. So it may indeed have once been habitable. And if so, in order to answer this question of whether or not life emerged on Mars, we have to start searching for evidence of that past life in the form of biosignatures, the things that life left behind in the rock record that we can study today. And so Jezero crater, the landing site of the Perseverance rover, was chosen for a very specific reason, which is that this crater is thought to have once hosted a river delta and a lake. So what I'm showing you on the left side is the Jezero crater, and on the right side is an image from Earth, the Yukon River Delta. And you can see that these deltas, when a river is entering a large body of water, it creates this kind of fan shape. And we see exactly those types of structures in Jezero crater, this river inlet that's entering the crater and then sort of fanning out to create that delta deposit. So that indicates to us that Jezero crater might have had standing bodies of water in it at one point. So it's a really prime location to look for evidence of past life. It might have lived in this type of environment on Mars. So then if we have an environment on Mars that we think might have been habitable in the past, how do we search for signs of past life, evidence that life existed in that type of crater in the past? Well, on Earth, we learn about past life by looking at the fossil record. So when I say fossil, these images are probably the images that pop into your mind, things like shells and dinosaur bones and trilobites. And so those are more kind of complex organisms that have what we call hard parts. They have mineralized components. A shell is made up of minerals, teeth and bones are made up of minerals, and those hard parts of the organism are very easily fossilized, and they're easy to identify in the rock record. But in addition to all of the complex life that we have on Earth, the Earth is also really kind of dominated by microbial life. And so what I'm showing you here is this little microbial mat. So these are, if you go out into any kind of pond or river, you see what people would call maybe pond scum. It's like these kind of fuzzy, scuzzy green mats. And those are cyanobacterial biofilms. So cyanobacteria are a special type of bacterium that is photosynthetic. And that means that it can make its own food using light and water. So this over on the right side is a zoomed in version of those cyanobacteria. And these are very abundant on our Earth and really drive kind of life and life cycles on Earth as primary producers. But these types of microbial organisms are really soft and squishy. They don't have those mineralized hard parts like the more complex organisms. And as a result, the biosignatures that these types of microbial organisms leave in the rock record are harder to identify and understand. So I want to talk for a minute about this concept of preservation potential. And that's simply the potential for a biosignature to become fossilized in the rock record. And that fossilization process requires minerals because squishy organic compounds can degrade really rapidly and they don't get preserved in the rocks quite as easily. And so an organism with those hard parts has a high preservation potential. Something like this snail, its shell has a high potential to get preserved. But organisms that are soft and squishy, these kind of microbial organisms, have a much lower preservation potential. And this becomes problematic when we think about deep time, ancient history of a planet, because those complex organisms that make those hard parts and mineralized components that can be preserved didn't evolve until very recently in Earth history. So this is a timeline of Earth history going back from the modern over here on the right, all the way back to the formation of the Earth 4.5 billion years ago. And complex life didn't evolve until this tiny area right at the end. And prior to that, our planet was dominated by microbes. And when we compare that to the history of Mars, this Mars that we see today that's very dry and arid and not very habitable, that extended back about 3 billion years ago. So Mars wasn't habitable until very early on in its history. And if we compare that to the type of life that was living on Earth at that time, the life that we can expect that might have been preserved on Mars is probably microbial. It's probably not that complex life with all the mineralized bones and teeth. So then our task becomes very challenging, because not only are we trying to search for signs of past life on another planet, we're trying to search for signs of past microbial, microscopic life buried in the rocks that might not have been preserved very easily. So then how do we learn about that kind of past life? Well, there's this really magical thing that happens in nature, which are microbe-mineral interactions. Microbes are constantly interacting with the environment around them. So what I'm showing you here on the left side is a stromatolite, a modern stromatolite in Shark Bay. And a stromatolite is a microbial and mineral structure that builds in different environments on Earth, in marine environments and lake environments. And as the microbes make these microbial mats, they trap and bind minerals, or they help to form minerals around the layers of the mats, and then create these kind of concentric layers of mat and then minerals and mat and minerals. And over time, that becomes preserved in the rock record. Over on the right side is an ancient version of stromatolite that's preserved in the rock record. And so those minerals are forming and encasing the microbes and the biosignatures. And two minerals in particular are really important for that process: carbonate and chert. And I'm going to focus on chert for the purposes of this talk. Carbonate is also really interesting, but chert is kind of near and dear to my heart, and I've done some experiments that will show you why. So what is chert? Chert is a microcrystalline silica, SiO2, so it has silicon and oxygen. And chert can form many different ways. What I'm showing you in this image here is a rock outcrop. So think if you walked up to kind of a road cutting and you saw this sequence of layers of rocks on the side of the road. All of the tan colors that are layered here are carbonate rocks. And all of the black that's kind of punctuating it as little nodules and lenses, that is chert, silicon. And it's a special type of chert, because even though chert can form many different ways, either with or without life, the type of chert that I'm showing you here formed in tidal environments in the Proterozoic, so billions of years ago. And that type of chert preserves biosignatures really, really beautifully. So what I'm showing on the left side, this is a 2 billion year old biosignature. So these are microbial mats that create this kind of pustular structure. It's my least favorite term that I have to use in my research, but it's very descriptive of what they look like. So these are these ancient microbial mats. And if you zoom in on them, they have actual bacterial cells, microscopic cells that are 2 billion years old, preserved in the rocks. So this chert is preserving them, freezing them in time. And that becomes really important when we start to think about Mars, because we know from orbital observation that both carbonate and silica are present in Jezero crater. And so that means that these types of biosignatures that are preserved in cherts might also exist on Mars. So how will we identify those biosignatures then? If the rock types that preserve them might exist on Mars, how are we going to find them on the surface and determine whether or not they really do carry signs of life? Well, first, we have to understand how the chert formed in those ancient tidal flats, because not all chert is going to hold biosignatures. It depends very much on how it formed. And so we want to know what makes that chert different from the chert that does not preserve biosignatures. And we also want to know then, are there any distinct features or fingerprints of that biosignature preserving chert that we can use to help identify the rocks with the Perseverance payload? So we're searching for fingerprints that can help us find biosignatures and evidence of past life. And this is where my research comes in. So this is my Earth-based side of, oh, go ahead,
I
Jennifer.
have one question.
Okay.
How do you know it's 2 billion years old?
That is a really good question. I'll leave it on this picture because it's the same rock. So there are different ways of dating rocks and determining how old they are. A lot of times we use radiogenic isotope dating. So some of you might have heard of carbon dating, where you look at the radiogenic carbon and it decays over time to the stable version of the carbon. And that's how we date things that are, from ancient human history. And something that's 2 billion years old, we have to use different elements. But basically with these types of sedimentary rocks, they're often found in association with igneous rocks that contain minerals that we can date, that have those radiogenic isotopes. It's a little bit of a complicated process, but I'm happy to go deeper into it if anyone wants me to. All right, so the Earth-based research. So what I do to find the types of fingerprints that might be useful as we're searching for signs of life on Mars is I study the fossil record and modern microbes on Earth. And I do that to try to understand how the ancient organisms on Earth interacted with their environments and how the biosignatures were preserved in the rock record. And then use that information to find fingerprints that might tell us about microbes and ancient organic matter and biosignatures in the rocks that we can use for Mars. Okay, so I'm going to explain a little bit about what we do and do not know about chert in ancient rocks on Earth. So imagine that you're standing out on a beach in the Bahamas, for example, and all the white sand that's beneath your feet, that's all carbonate minerals. And over time, that sand on the beach is going to pile up and turn into carbonate rocks that we see in the rock record. But if you were on a beach like that 2 billion years ago, you might see all these little tidal pools on the beach that contain cyanobacteria and other types of microbes. And over time, those little tidal pools that have the microbes in them became silicified. So silica accumulated and precipitated. It formed a solid substance from the water and encased the microbes. And then the result is that black chert that's within the carbonate that we see in the rock record. So that's kind of a simplistic view of what we think happened, but we don't actually know kind of the nitty-gritty details of this. And there are a lot of question marks for us still. And the reason is that in order to preserve these types of microbial cells, you can see some of them are even dividing here, to preserve cyanobacteria or any other microbe on that kind of timescale, almost instantaneously, the minerals had to precipitate very, very rapidly around them. And so that requires very, very high levels of silica to be dissolved in the water to precipitate out that way. And we know that ancient oceans had more silica than modern oceans do, but it wasn't enough silica to precipitate abiotically, kind of spontaneously and instantaneously, as you would need to preserve these fossils, these cells. So something's missing from the story here. There's something that we're not understanding about how this process occurred. So to find out how that process occurred, I conducted fossilization experiments. So there are modern microbial organisms, modern cyanobacteria, that look very similar to these fossils that make these pustular mats. So down on the bottom here, you can see the modern versions that make those pustular microbial mats in little tidal pools on the beach. And if you zoom in on them, you see these little cells in here that have these layers of envelopes around them, and they look very similar to the fossils. So I took those microbes and I put them in seawater that looked similar to ancient seawater, where I added silica, but not enough silica that it could just spontaneously precipitate on its own. And then I just watched what happened, saw how the cells behaved and what the result was. And here are the results of that experiment. So after just one day, the cells didn't have very much silica around them. So what I'm showing you here is a scanning electron microscope image, or SEM. So this is a type of very high resolution microscopy that allows us to see individual cells inside of the microbial mat. And then it also has this function called EDS, which allows us to quantify the elements that are present, figure out what elements and what distributions are on the mats. And after this one day of exposure to the seawater, the cells didn't accumulate very much silica. But when we left them in the water for 30 days, the cells turned out to kind of retain their plump shape, and they were coated in this little coating of these tiny microscopic nanoparticles of silicon. So over time, what was happening in these experiments is that the microbes were helping to pull the silicon from the water around themselves and kind of create their own shells. And when you zoom in a little bit more, here are what some of those little precipitates look like. We found out that they were not only rich in silicon, but they're also rich in magnesium. And that is going to become really important later on in our talk, because it appears that the cells need magnesium to coat themselves in silica and become preserved. And this is how we think that this is happening. So this is my little cartoon version of my experiments, where the green thing over here is a cyanobacterial cell. And organic surfaces are very commonly filled with sugar polysaccharide compounds that carry a negative charge. And then in the seawater all around those microbes, there are cations, which carry a positive charge, and anions, which carry a negative charge. So the silica that's dissolved is a negatively charged compound. So if you have a negatively charged cell and then negatively charged silica, those negatives are going to repel each other. They won't bond together very easily. But when you add the magnesium into the mix, it acts sort of like a bridge, and it helps to bridge the gap between those silica compounds and the organic surfaces, and then ultimately results in the formation of this cation-rich silica that's preserving the cells. So I'm going to pause here and summarize what we've talked about so far before I dive back into Mars. What I've shown you is that chert can form through a variety of mechanisms that may or may not involve life. But this one very specific type of chert that forms in tidal environments formed through a mechanism that may have been mediated by microbes billions of years ago in these tidal environments. And this specific mechanism that preserves biosignatures requires cations like magnesium to interact with the organic surfaces in the silica. So how does that help us find life on Mars? Well, if there is silica on Mars, like we have identified from orbit, it may have formed through a similar process. And if we know then what the biosignature preserving silica mechanism was, then we can probably be better equipped to target those rocks and figure out whether or not they might host life. And this is really important because not only is the Perseverance rover driving around and exploring Jezero crater, it's also picking up samples that will be brought back to Earth and studied here. And so one of the aims is to identify rocks that have a high potential to carry biosignatures and then put them in the sample cache and bring them back. So if we have a way to identify the rocks that have a high potential to preserve biosignatures, we'll be able to study them once they get back. And based on the research, one thing that we might be able to look for is cations like magnesium and organic matter as indicators. So my hypothesis then that I wanted to test is that I found all of that mechanism with the cations and the magnesium using modern experiments, but I wanted to then look at ancient chert and see if it carried signs of that kind of magnesium or cation enrichment. So I hypothesized that ancient chert on Earth that preserves biosignatures may have formed through a similar mechanism and carry those kinds of cation signatures. And so to test that, I analyzed some chert from Earth. So this is a hand sample of that chert. It's about 1 inch wide, and you can see all the dark spots in here that look like kind of wavy structures, linear structures. Those are the microbial mats. And we took that chert and stuck it on a scanning electron microscope. So this is what one of those SEMs look like that I was telling you about earlier. And I analyzed them to find those cation signatures. And here's what we found. What I'm showing you here is on the top left, the scanning electron microscope image. So this is a black and white image generated for us, where all of these kind of angular structures all around here are the minerals. And then this dark kind of fluffy blob that's in the center of them, that's organic carbon, organic matter, the biosignature from 2 billion years ago. And then using the elemental mapping capabilities of the SEM, we could map out carbon, the basis of that organic matter, and then also calcium and magnesium. And what we saw is that the chert that contained these biosignatures, the organic compounds, are enriched in calcium and magnesium. So that's really exciting for us because it tells us that cations in chert may be an indicator of biosignatures, and that's something that we can search for as our fingerprint on Mars. But one of the problems is that I found that on the Earth samples using an SEM, and we don't have an SEM on Mars. Hopefully in the future, one day we will. But what we can do is combine two of the instruments that are on the Perseverance payload to search for those same kind of fingerprints. So I'm going to pause here for a second because I'm sure some of you are curious about the Perseverance rover and the instruments on board. So I'm going to run through these really quickly. So the one down on the bottom here, MOXIE, earlier in the talk at the beginning, I said that part of the mission was to plan for future human exploration. And the purpose of MOXIE is that it's an instrument that can generate oxygen using Martian CO2. So we're trying to see how well we can produce oxygen on the surface of Mars for future human exploration. Over here, we have RIMFAX, and RIMFAX is a ground penetrating radar, so it can tell us about the rock structures that are below the rover's wheels. Up on the top, we have Mastcam-Z. There are several different cameras on board the rover, and Mastcam-Z is one that gives us these beautiful panoramas. I highly encourage anyone to go and look on the NASA website, and you can see these beautiful panorama images of Jezero crater that are taken by Mastcam-Z. Supercam up here has a really high resolution micro-context imager, and it also has some different lasers that can analyze rocks from far away. And META is our weather station. So META is monitoring the atmospheric changes, it's monitoring wind, it's monitoring temperature to give us an idea of all of those different fluctuations on the surface of Mars. And then the two that I'm going to focus on that are out here on the end of the robotic arm are Pixel, which is an X-ray spectrometer, and Sherlock, which is an ultra deep UV Raman spectrometer. And I'll talk a little bit more about those in a minute. Okay, so here's Sherlock. Sherlock is, NASA likes to have their acronyms. So Sherlock is one of the longer ones that we have, and it stands for Scanning Habitable Environments with Deep Raman Luminescence for Organic Compounds. And so Sherlock is, as I said, a Raman spectrometer. And for those of you who don't study Raman spectrometers or physics or chemistry, this instrument detects different molecules in the rocks. So what I'm showing you over here on the right is a spectrum that an instrument like Sherlock can collect, where each of the different peaks that it shows you tell you something about the compounds that are present in the rock, the different molecules, either organic compounds or minerals like carbonate or sulfate. And then Sherlock can also map those compounds on the surface so that we can see how they're distributed and look at the textures in the rocks. And then Pixel, which stands for Planetary Instrument for X-ray Lithochemistry. Pixel is an X-ray fluorescence spectrometer. And so Pixel can detect different elements, where Sherlock is looking at molecules, Pixel is looking at elements like calcium, iron, magnesium, silicon. So it has the capability to find these and map them on the surface as well. And these are the specific kind of elements that we're interested in to see if chert containing cations is a biosignature on Mars. So since we don't have an SEM on Mars and we can't identify these types of biosignatures using the approach that I use on Earth, we wanted to sort of ground truth this method and take those same rock samples that I had analyzed and analyze them in a Perseverance Rover style and see if we could detect the same biosignatures. So using Raman spectroscopy, so this is a sample of that same chert that I was analyzing earlier, but this is a more zoomed out version of it, something similar to what any of the cameras on the Perseverance rover would see. And we analyzed one of the darker regions of the chert and one of the lighter regions. And what the spectrum from the Raman spectrometer shows us is that in the darker region, there are these peaks that tell us that there's organic carbon present. But in the lighter region, those peaks don't exist. So this is showing us that there are organics, and it's showing us where they're distributed in the rock. And then when we analyzed that same instrument using XRF, like Pixel, we detected that there's silicon everywhere. This is a chert, so there's silicon all over the entire surface. But when we looked at calcium, which is a cation like magnesium, the calcium tends to be concentrated in those darker regions. And so when we put those two data sets together, what we found is that using rover-like instruments, using Sherlock and Pixel, we can detect these types of cation and organic rich chert samples. So if we see these types of signals on Mars, these are the types of samples we might want to select for sampling and return to Earth.
I think this is a good point for the question.
Definitely.
Is there any chert on Earth that isn't correlated with microbial life? If we do see something like this on Mars, is it a definite pointer to processes involving life?
Excellent question. So there are chert deposits on Earth that did form without life, especially if you go back into the Archean, so even older than the rocks that I've looked at. There are huge like beds of chert that we see in the rock record. And those formed very deep in the ocean, usually in association with iron. And that was through a purely abiotic process, so formed without without life. And then the chert that forms in tidal environments, it doesn't necessarily have to involve life. And what we have seen in our research is this sample is a good example of that, where this lighter region is chert, but the chert in the lighter region didn't necessarily form through that organic interaction. And it might have formed as a later process that came in and altered the rock after it had already been deposited. So that's why just seeing any silicon or any chert on Mars is not necessarily a good indicator in and of itself for life. We need these additional lines of evidence. So to conclude, what I hope I've convinced you of here is that Proterozoic tidal cherts may have formed through interactions that I just described, these interactions between microbes, cations, and silica. And what that tells us then is if we understand the mechanism by which this formed, we can understand what fingerprints that mechanism might hold in the rock record. And we know that silicon, calcium, and magnesium are good indicators or pointers to show us where the biosignature holding rocks are. And not only can we detect those on Earth, but we can actually detect these same types of biosignatures using Perseverance type rover instruments, using Pixel and Sherlock. And so what I hope is that if similar biosignatures to these do exist in Jezero crater, I think that we might be able to find them and identify them. And I'm really hoping that we can collect them and bring them back to Earth at some point in our lifetime so that I can study them when they get back. And with that, I'd like to thank my funding sources, my advisor, John Gratzinger, and all of my collaborators, as well as the Pixel and Sherlock instrument teams and the Mars 2020 team, and Amanda and Jennifer for hosting me here. It's been really fun to be a part of this, this whole festival. Thank you.
Yeah, thank you, Kelsey. That was really enlightening. So for those in the audience, please start typing questions into the chat box and we'll be happy to pass them along to Kelsey. To start, I have a few questions. So how would Supercam and the LIBS elemental analysis fold into some of your observations?
Yeah, great question. I'm going to flip back to one of the rover pictures so that I can show everyone. Okay, so Supercam up here that I said had a laser. So what Jennifer mentioned, LIBS, that's one of the capabilities of Supercam. And that is one of the cool things about Supercam is that in contrast to Pixel and Sherlock, which have to be right up against the surface of the rock to collect any data, Supercam can collect data from about 7 meters away from the rover. And it does that by shooting this light. This is what LIBS does. It shoots this laser at the rock surface and ionizes all of the elements at the surface. So it kind of blows up the elements from away from the rock. And then its detectors can detect what elements are scattered away from the rocks. And so I think that all of these analyses are really relevant for LIBS because if we see a rock from a distance and we shoot it with Supercam and we see that it has silicon and calcium and magnesium or any of those combination of elements, then that would tell us, okay, we should drive that way. Let's go over to those rocks and get Sherlock and Pixel right up against them. Because as we're driving along, I mean, Jezero crater is huge, Mars is huge, and we have this one tiny rover that's driving very slowly on the surface. And there are only so many rocks that we can analyze right up close. So our ability to use something like Supercam and analyze the rocks from far away is really important.
Cool. And then a question about the cations. So
Yeah.
you showed magnesium and then you also showed calcium.
Mm-hmm.
Both of those are 2+ ions. Is there a reason for that, or could it be other cations too?
Yeah, that's a good question. I don't know why it is. I was going to try to find you a picture of it, but maybe there it is. So in my experiments, I have tried, I'm using seawater. So seawater has a ton of sodium in it, which is 1+. And the sodium is never really playing a role here. The sodium doesn't bond to the silica quite as well. And so I don't know if it's something about the way that the 2 positive charges of the magnesium can bond to the organic surfaces and the silicon, or help to complex more of the silica molecules to it. Maybe it has to do with the size of the magnesium compared to the sodium or other elements. Yeah, but it really tends to be magnesium. Calcium can do it to some extent, and we see that in the rock record. I think iron probably does this. I don't typically use a lot of iron in my experiments, but maybe if we're studying Mars, we should, because there's a lot of iron there.
Yes.
Yeah.
And then where do you think the cations would come from on Mars, right? Are we thinking about it similar, like an oceanic, a saltwater composition? Can you look for other salts elsewhere to maybe constrain what, the formation of these organic cherts?
Yeah. So there are a lot of question marks surrounding Jezero crater and the lake that might have existed in Jezero crater. And one of them is, what did the water look like? Was it saline? Was it freshwater? What was the pH? What was the temperature? And so we don't know the answers to any of that yet, but using these instruments and studying the mineral assemblages, we should be able to start to answer that question. What did the water look like? But in addition to that, we do know that a lot of the rocks that are being weathered, so the rocks that are being kind of crumbled up and redeposited inside of the crater and being dissolved and having all of their compounds put into solution, those are basaltic rocks, source rocks. So basalt, just like the basalt that we have on Earth, and it contains a lot of the different elements that would be relevant for these types of processes.
Cool, thanks.
Yeah.
So we have a question from Christian. Thank you. Were there other locations considered for the Perseverance mission? Where would you like to see future rover missions go?
That's a great question. We'll use this one, this picture of Jezero crater. Yes, there were a lot of landing sites that were proposed. And this was one of the most fun parts of my PhD experience, I think, is seeing kind of how democratic this process is. So all of the different landing sites, NASA didn't just kind of unilaterally make a decision that this is where we're going to go. They asked scientists from institutes all over the world to present their ideas of where they wanted the rover to land. And then there was a series of conferences that happened where people would present their ideas and try to argue their case for why they thought the rover should go to their specific location. And then the scientific community would vote on where they wanted it to go. And it kind of got narrowed down. So I got to attend one of the meetings that was in, I think it was the final 3 landing sites, and then vote on which one of those final 3 we wanted to go to. And Jezero crater was the one that I voted for. So I was excited to end up here.
Where would you like to see future rover missions go?
Oh, that's a good question. I think, it's always kind of a toss-up between, do we go somewhere that we've never gone before, or do we go somewhere that we have been, but with newer capabilities and newer instruments that can do a little bit more? And I think that in some of the places that we've already visited, places like Gale Crater, there are still a lot of unknowns there because the instrument payload that we have doesn't do exactly the thing that we need to answer the question. So I kind of want to go back to some of those places. We've already got some idea of what the rocks are and how they formed. And I think going back with a different set of instruments, we might be able to dig into that a little bit more.
We just need to send like a bunch more missions, right?
Yeah, exactly. And hopefully get an SEM into space one day.
Oh, that'll be interesting. Are there portable field SEMs now?
There are people who are working on making them, like little tiny ones, but they're hard to operate. So getting it to operate by a robot is challenging.
Maybe when the astronauts get there.
Yeah, definitely. We'll bring one with us.
Okay. We have another question from Stephen. Could we see similar fossilization anywhere else in the solar system?
Possibly. I think it's both a question of, are there other planets that could have been habitable? And if so, do they have the types of rocks that could hold these types of cation signatures in chert? And there are a lot of moons in our solar system that might have been habitable or might be habitable, some of the ocean worlds. We don't know a lot about the rocks and the minerals that are in those types of ocean worlds. So it's a really good question, and I don't have a definitive answer for you, but maybe.
Great. Let's see. So please continue to type your questions if you have any, but in the meantime, I will ask Kelsey, what area of the crater are you most interested to explore?
Yeah, I'm gonna flip back to the bigger version of, there we go, of Jezero. Yeah, so I didn't talk very much about, actually, you know what, I'm gonna go back to the very first slide because that one's the biggest one. We can explore Jezero crater together. Yeah, I didn't talk very much about kind of where the rover is currently and where it's going. So kind of try to orient yourself on this map. So this rim right here is the crater rim. So that would have been kind of the lake shoreline if there was an ancient lake here. And then this little snaking valley that's going in is the river that was bringing the delta in. And then this whole fan of rocks here is the delta deposit. And then everything else kind of over on the right side is the crater floor. And Perseverance, those of us who are geobiologists and astrobiologists, we were kind of hoping that the rover would land close to the delta over here. And that's because delta deposits are known to be really good places to search for organic compounds and biosignatures in the clays that they deposit and bring in the sediments. And that's also these areas right around the delta are where those carbonate and silica signatures were seen from orbital data, and then right along the crater rim. And it turned out that the rover landed farther into the crater. So right here, there's this kind of oven mitt shaped feature on the crater floor, and the rover landed about here. So we just only kind of traversed this little area right in the crater rim. And we're just about to start this long campaign where we're going to drive around that area and then drive up for the delta. And what we've seen of the rocks so far is that it looks like the crater rim is mostly igneous rocks. So basaltic rocks or other kinds of igneous rocks that formed through totally abiotic mechanisms in environments that probably didn't host life. So these predate the lake most likely and don't really hold biosignatures. So I'm really excited for the part where the rover gets to the delta front after this long drive that we're about to take, and we start analyzing the rocks over here.
And how long is that going to take?
We're starting that long drive right now, and it looks like it's going to take about 2 months.
Okay.
Yeah.
Well, it's already been a year, so 2 more months is
it's
nothing.
Like nothing. Exactly.
Okay. Well, if there are no other questions from the audience, last call maybe. Yeah, well, thank you so much, Kelsey. This has been just really fascinating, and we really appreciate you taking the time to discuss your work on the Mars 2020 mission.
Thank you so much, Jennifer, and thank you for hosting, you and Amanda and everyone else who's made this entire festival a reality.
All right, well, thank you, and good night, everyone.
Thank you.
Oh, let's see. We have one last question right at the end. Let's go for it.
Sounds good.
Art and Sharon ask, is there any other explanation for the delta in Jezero crater than water deposition?
That's a good question. We, based on the rock textures and structures and what we've seen, and we have some images that we've taken with Mastcam-Z and Supercam from far away that show layers in the rock deposit. So it really does look like a river delta is the most plausible explanation.
Kind of similar to maybe like New Orleans and the Gulf there, right? Yeah, they're similar, I think. Yeah, and then another question here actually from Zach. How fast is the rover?
It's not very fast. I don't know exactly what speed it's traveling right now. We had to test out some of the autopiloting early on in the mission, but it only covers, a few dozen meters over the course of a few days. So it's very slow.
Right. Want to take our time and see everything, right?
Exactly. Yeah. And make sure that the rover doesn't, hit anything dangerous. We want to keep it alive for as long as we can, keep it going slowly and carefully.
Do you know much about the avoidance, the hazard avoidance software?
I don't know a lot about the software, but I do know that a lot of the cameras that we have on board are all these different like hazard cams and things like that. And there are engineers on the team whose specific job it is to make sure that we don't run into anything or break any of the instruments or go into areas that are too dangerous for us to try to traverse. So,
right.
We're situated over here and the delta's here. So the quickest way to get there would be in a straight line and just drive through this structure. But when you get right up close to it, it's filled with dunes that the rover can't traverse over. So it was determined that that was too hazardous of an area and we have to go around.
Right. So it can't be too rocky or too sandy.
Exactly. Yep.
I think that's what happened to Spirit, or was it Opportunity? One of those got stuck in some sand, I think, right? So, yeah. Okay. Well, that's fascinating. I hope that we get to the Delta soon. I agree that I think that'll be very, very fascinating, and I can't wait to see what comes out of it.
Yeah, absolutely.
Okay. Well, I think that is actually the end of our questions. But yeah, thank you to everyone out there who was listening and asked questions, and thanks again to Kelsey.
Thank you so much.
Yeah.
All right, I'll go ahead and stop sharing my screen now.
All right. Thanks, everyone.
Thank you.